So this is Sikdar 1 brought to you by Aerospace LLC. This is our mission overview. We're trying to get a 5-person crew on Mars to study plant growth in Martian soil so that in the future when we do colonize Mars, we can see if we're able to grow the food there, which is important because if we can't grow food, we're going to die. So this is our timeline. For the first around 10 months, we're going to be going to Mars since the trip takes roughly around 9 months. And then after that, we're going to immediately start methane production and O2 production using the Sabatier reactors since it'll take a long time to do so. And in the meantime, we're going to start doing the plant growth experiments using hardy crops like beets, potatoes, and different types of grains. Then after that, once our fuel production is finished, we're going to ascend from Mars and then return to Earth.
As the biosub team, our goal was to design life support and other systems that would give a group of 5 astronauts the ability to survive for 32 months on our mission to Mars, and 32 months is the full duration of the mission. This required us to come up with specific goals, which included just calculating the amount of required food, designing an oxygen generation system and a way to remove this excess CO2, and designing a way to get water. All of these required us to calculate the amount of resources that would be used by the team of 5 astronauts. And we were also responsible for designing the Mars soil experiments, which was the purpose of our Mars mission. The water recycling system processes water in 4 different parts. The first is the collection stage, which is where the water is collected after it's been used through terms of like urine, sweat, exhaled water vapor, wastewater from hygiene, and condensation. And this can be done through multiple different mechanisms, including specialty toilets and condensing heat exchangers, which capture the water from when hot gases cool and condense. The next step would be the water would be sent to purification through either the urine processor assembly or the water processor assembly, and then it would be sent to be stored and reused, and back the cycle starts again and where the water is used. This specific system can process about 2.4 gallons per day, and that would be enough to support the crew of 5 and process like extra water. It's enough to support the crew of 5 and additional water usage just in case. And so we would run this about once a day. The urine processor assembly functions as a specialized vacuum distillation process, and that's necessary because in space water doesn't boil properly due to the different gravity. The urine processor assembly uses a vacuum pump to lower the atmospheric pressure in the system, and that reduces the liquid's boiling point. Then a rotating drum helps separate the water vapor from urine and keeps solids from clogging the system. The water vapor is then sent through a filtration system, and then organic contaminants are removed with either phosphoric acid or hydrogen peroxide treatments. The water processor assembly functions by sending water first through filter beds, and that removes organic compounds and other things that could be harmful for human consumption. Then the water goes through a catalytic oxidation reactor, and that breaks down any remaining organic compounds. Hydrogen peroxide is then introduced into the water and then breaks down using a catalyst, creating oxygen that oxidizes or destroys organic contaminants. Then the water is sent to ion exchange beds, and these remove charged metal ions by releasing either hydrogen or hydroxide ions to remove either positive or negatively charged metal ions. And then the water processor assembly adds in small amounts of iodine, and that is to prevent bacteria growth for when the water is stored. For our mission, we calculated approximately 1 gallon per person per day to be for usage in either consumption, hygiene, food preparation, and other different water usages that they would need. This water processing system has about a 93% efficiency, which means that over the course of the entire mission, we would lose approximately 155.2 gallons. And going off of the 1 gallon per person per day, we would require at a minimum of 160.2 gallons. And this does not include any of the water from the Mars soil experiments.
Radiation shielding defends crews and sensitive electronics from dangerous ionizing radiation like galactic cosmic rays and solar particle events, to name a few examples. There are two different forms of shielding, passive and active shielding. Passive shielding uses physical mass to absorb or scatter incoming radiation without generating harmful secondary particles. Materials with high hydrogen content are most effective because hydrogen nuclei efficiently stop high energy particles. Water can also serve as a radiation shield, and also sometimes designs are made around the sleeping quarters to protect astronauts during solar flares. For our specific project, we are going to have to use active shielding because this is for long-term deep space exploration, and traditional passive shielding is too heavy to carry practically for this trip. There are two different types. We have magnetic fields and electrostatic fields. Magnetic fields uses high-temperature magnets or pulsed electromagnetic fields to create an artificial magnetosphere around the craft, mimicking Earth's protection. We also could use electrostatic fields that pushes the charged ions and protons away before they can penetrate the hull. These are both very good forms that we could use, and we'll look into that later in the future.
Unlike Earth soil, Mars regolith is fragmented basaltic rock pulverized by eons of meteorite impacts. Its porous basaltic dust lacks the adequate organic structure of soil for planting. It contains no organic matter, no moisture, and no microbial life. Mars regolith is abundant in iron, magnesium, calcium, and phosphorus. However, it lacks potassium and nitrogen, the essential pillars of plant growth on Earth. Martian soil also has a toxic composition. The Martian surface contains 0.5 to 2% perchlorates. These salts are highly toxic to human thyroid function, lethal to most Earth-based microorganisms, and a major chemical inhibitor for seed germination. Mars soil is also slightly alkaline with a pH of 8.2. While manageable, it influences nutrient bioavailability, and most Earth crops prefer a pH of 6 to 7.5. To address these issues, we have several remediation strategies. First, we can use water leaching, which involves flushing the regolith with water to dissolve and remove soluble salts and perchlorates. We can also do bioremediation, which is using perchlorate-reducing bacteria to break down toxins into harmless chloride and oxygen. We can also use thermal treatment, heating the soil to decompose the perchlorate. Though this is energy-intensive for large-scale farming, it is feasible for our experiments of seeing if farming on Mars is possible. Once the regolith is prepped, we can introduce and plant pioneer species such as alfalfa and clover. They won't be used for food, but rather to naturally pull nitrogen into the ground and provide essential biomass for future composting. As for the pH, we plan to test sulfur-based amendments to slightly acidify the soil for optimal nutrient uptake. Our primary harvest selections focus on caloric density and rapid growth. Potatoes are high-density carbohydrates and are easy to grow in regolith mix. Kale and spinach have high vitamin yields and oxygen production. Radishes have a quick 25-day turnaround for fast nutrients. If we are successful in planting on Mars soil, we will open opportunities to upscale and develop a self-sufficient colony. By utilizing a closed-loop bioregenerative system, we can maximize resource utilization and nutrient recycling.
And then this is the structural team by me, Vijay, and Callie. We decided to use the base vehicle of Starship 3 because it's theoretically proven to work for Mars flights. It has a built-in lander, so we don't have to do the work of designing that. And it's meant to transport 100 people, so we could easily fit 5 in there, and then the food required for the whole journey. And the fuel is synthesizable on Mars, which is important because we want them to return home. And the cons is that, unfortunately, we need to do orbital refueling in low Earth orbit, and we have some constraints with our modified design since it's not meant for adding a nuclear reactor and ion thrusters and such. These are the specifications. And the propel capacity, this is enough to get us off the Earth because we're going to be using this super heavy booster here. And that'll do the brunt work of getting us to low Earth orbit, and then we can do our engine burn using this actual Starship 3. And we wanted to pick this we wanted this payload capacity of 100 tons because that gives us enough leeway and a lot of room to pack whatever we need for the mission. And this thrust should be enough for getting off Earth and Mars. And you can see that the propellant capacity is 1,600 in tons, and the tons of force is also 1,600. But we have to keep in mind that on Mars, the gravity is lesser, and so the weight force will be lesser. So our thrust to weight ratio will actually be greater on Mars. And because we're using nuclear reactors, we have to radiate away the heat because in space, there's no medium. So the only way to remove heat is through radiation. So we're using these radiators covered in black because black absorbs and emits the radiation the most compared to any other color. And to minimize heat coming in from the sun, we're going to rotate them so that the edge of the radiator is always facing the sun. And that minimizes the area getting heat in. And we can use both sides of the radiator to expel heat. And we also may need to increase the space inside of Starship 2, which will be easy because there's around 614 cubic meters of space, and this is designed for around 100 people. So we're going to remove around, this should be 450. I'll change that later. But this should be around 450 cubic meters, which is enough for our crew of 5 since NASA's standard is 30 meters cubed for each person. And now for the CS robotics team, which is Andy, Jason, Sharon, Jofi, and Ariana, and the trajectory team, which is Adrit, Gage, and Krithi. So the trajectory design, they decided to use a Hohmann transfer since trajectory that used the least amount of energy, and propellant because we're not trying to carry a bunch of it just for a faster trip. We need an escape velocity of about 11.2 kilometers per second, which we're going to do with our super heavy stage. And on the transfer, we're just going to cruise with the ion propulsion for a shorter transfer time and to make the micro adjustments. Our parameters is that our total liftoff mass maximum is going to be 5,300 metric tons, and our liftoff thrust from the super heavy phase is going to be 75 meganewtons, and the Mars thrust from the Starship 3 is going to be 16.5 meganewtons. And in both cases, we will be able to lift off since our thrust to weight ratio is a lot greater than 1. And to make the simulations for the CS team, they decided to either use RocketPie or polyastro, and they ended up using polyastro because RocketPie is more for like designing the rockets in detail and adding aerodynamics and stuff like that. But polyastro, we decided that would be more important because we just want to get the orbital mechanics of it, and it had its own built-in orbital mechanics tools. Aerodynamics wasn't really a factor. And this is the Earth to Mars simulation that they made in polyastro. You can see that over the process of 259 days, which is around 9 months, we go from Earth to Mars, and at this intercept point down here.
The propulsion team is Vasudevan Govardhanen, Joel D'Souza, Daniel Altman, and Samir Patil. Our mission uses nuclear electric propulsion, or NEP, for the journey between Earth and Mars. A compact fission reactor generates electricity, which powers several Hall-effect ion thrusters. These thrusters ionize xenon gas to produce thrust. While they generate much less thrust than chemical rockets, they are far more fuel efficient, making them ideal for long-duration missions. We also include multiple thrusters for redundancy. So how do we use this system throughout the mission? We launch from Earth using Raptor 3 chemical engines, which provide the high thrust needed to escape Earth's gravity. Once we're in deep space, the Hall effect thrusters take over. They operate continuously during the cruise to Mars and perform small trajectory correction maneuvers all along the way. As we approach Mars, we switch back to chemical propulsion for orbit insertion and landing, since ion thrusters don't produce enough thrust for those maneuvers. This hybrid approach combines the power of chemical rockets with the efficiency of electric propulsion. The entire system is powered by a compact fission reactor producing 200 to 400 kilowatts of electricity. That power runs the Hall effect thrusters as well as onboard systems like life support, communications, and scientific equipment. Because the reactor generates a lot of heat, deplorable radiators dissipate that heat into space. Together, this gives the spacecraft a reliable power source for both the trip to Mars and long-term surface operations. Thank you.
Hello, this is the Finance, Legal, and Ethics team presentation for the Mars project. Our estimated costs for this project are about $500 billion at most. For the development costs, we estimate that the Starship class vehicle would cost around $15 billion, the Deep Space Life Support would cost $17 billion, the ECLSS, or the Environmental Control and Life Support System, would be around $2 billion, and the NEP reactor would be between $900 million and $2 billion. Previously estimated program costs have been between $120 billion over 15 years and even $500 billion as estimated by the former NASA Deputy Administrator. For this project, we estimate that the recurring mission costs would be multiple tanker launches per mission, orbital refueling, 32 months of continuous ground operations and mission control, crew training with post-mission lifetime and medical insurance with monitoring, as well as contingency reserves of perishables and consumables, as well as required spare parts. For the budgeting and funding for this project, we estimate that we can get funding from national space agencies, international partnerships, commercial aerospace partners, as well as research grants. Moreover, for this project and its cost reduction plans, we aim to use reusable launch systems, recycle water and air, conduct partial food production on Mars, and work on shared international funding. Some of the financial risks that we have projected are launch delays, equipment failures, mission extensions, crop experiment failures, as well as supply shortages. The respective mitigative practices would be a good schedule with budget reserves, reducing redundant systems, creating emergency funding reserves, having multiple test crops and backup plans, as well as a safety stock and multiple recycling systems. Our legal considerations for this project was mainly the international space law, particularly the Outer Space Treaty that was signed in 1967 and the Artemis Accords that were recently signed in 2020. Our requirements are that we need to be using Mars peacefully and only for research without staking any national ownership claims while also taking responsibility for our mission activities. We are required to make sure that Mars is not affected by our activities whatsoever, and in the case of any damage, mission sponsors, the state, as well as our company, Aerospace LLC, is responsible for the damages. For the ethics concerns, particularly in the case of environmental damages, we are concerned that there's already a lot of debris on Mars, and a crewed mission would only increase the contamination by many orders of magnitude, which is why, in consideration of possible alien life, we've avoided introducing Earth organisms to the environment by using contained greenhouse systems, and we aim to conduct biological surveys before experimenting on a large scale. All the crew members are also going to be informed of the environmental rules of conduct, where they're not allowed to where they're supposed to minimize surface disturbance and manage waste and waste disposal, limit unnecessary resource extraction, and constrain crop experimentation to certain areas known as special regions, and understand that any debris and chemicals released are all considered contaminants. In terms of human ethics and crew welfare, crew safety is our most important factor. We're focused on radiation protection measures, emergency medical capability due to the limited staff on board, and mental health support during the long, isolated journey. It's important for all the crew members to have informed consent, where they must understand the risks of the mission and understand that all the risks must be minimized where possible, since the crew's safety is the most important. Our most dangerous factor is the radiation, since the potential radiation levels for this project are around 930, which exceeds NASA's career limit of around 650. This would require each crew member to sign a formal waiver to ensure that the crew members are informed and are voluntarily participating in this project. Safety is the most important to Aerospace LLC.